stating the domain and range of the current function. Then we're going to get the inverse and state its domain and range. And then we'll look at three ordered pairs just to kind of confirm that, yeah, all of our x's and y's truly are flipping. So if we look at number 39 from the homework, hopefully that we can look at this and we see that the parent function is the cube root function, and it's been shifted right 2 units. So if we were to look at this, we're hoping we'd recognize, okay, I'm shifted right 2 units, and I know that it's going to look kind of like that because of our parent function. Okay? Based on our sketch, we should be able to recognize that this domain and range, our domain is all real numbers, and our range in this particular case is also all real numbers. Okay? So when we go to take the inverse of it, how do you undo a cubic? How do we undo a cube root? Anybody? How do you undo a cube root? You cube it all. Good. So if we go to find our inverse, again, we flip our x and our y. So x is going to equal the cube root of y minus 2. To undo that cube root, we'll cube everything. So x cubed equals y minus 2. And then we can add 2 to both sides. So x cubed plus 2 will equal our y value. And so that becomes our inverse. And so the other way you'll commonly see that written is f inverse of x with that little -1. And that's our inverse symbol. Is going to equal x cubed plus 2. So hopefully when you look at this now, you're like, oh, well, that looks like our parent graph where we're shifted up 2 units. 1, 2. And it's a cubic function, so it's going to have kind of that basic S-bend, the normal way that we're used to seeing. Okay? So we start to see that, oh yeah, that is reflected across the line y equals x. And these inverse functions we start to recognize are going to be the inverse operation as well. So to undo a cube root, we want to cube it, so we would expect that those would be the same types of approaches. So when you look at this domain, okay, we're going to recognize that the domain of the inverse will be the same as the range. So in this case, it's all real numbers, which is to be expected. And the range is going to be what the original function's domain was. So again, we should expect this to be all real numbers. And as we look at the parent graph, that fits up. Okay. The last piece you'll look at is they want you to find 3 ordered pairs to prove that anything that was in the original as a comma b is now in the inverse as b comma a. So when you're looking at cube roots, what's a really easy number to take the cube root of? I think really easy. 9 won't work. 6 won't work. I think really easy. 27 will work. 8 will work, but 0. 0 is really easy, right? What's the cube root of 0? 0. How can we make a cube root of 0? What does x need to be? 2. So if I plugged in x equals 2, we would, when we plug in 2 equals 0, 2 minus 2 is 0, cube root of 0 is 0. Okay. So we know the coordinate point, 2 comma 0, which we see with our graph, exists. In the inverse, what point do you expect should be there? 0 comma 2. Good. So if I plug in 0 for x, we would expect 2 is going to come out. So 2 cubed is, 0 cubed is 0, plus 2 gives us 2. And we do see that, yes, in the inverse function, 0, 2 exists. And so they just want you to do this 3 times. So another easy number, like you guys were saying, was 27. What would I need to plug in to get to 27? 29. Good. So if I plugged in 29 for x, 29 minus 2 is 27. The cube root of 27 is 3. So we would expect in the inverse that the coordinate point 329 should exist. So if I plug in 3 for x, 3 cubed is 27 plus 2 is 29. And we start to see that that works out. Okay, so you'll do that for 3 coordinate points, and we'll see that this continues to match up, and we see all of our x's and y's flip. Okay, so that will be the first piece of things you see tonight. The next piece is going to be looking at restricting domains. Okay, so we've talked about how some functions are not one-to-one, and that horizontal line test helps us with it. So the inverse of it, so to speak, is another function. So anytime we look at a parabola, in this particular case, this is a parabola shifted left 5 units. So 1, 2, 3, 4, 5. And so we know that this graph will look something kind of like that. At the moment, that's not a one-to-one function. What we want you to do is restrict its domain, so reduce the x values such that it preserves all the range values, so I still have all of my y values, and then it creates a one-to-one function. So how can I reduce a parabola so I still have all the same y's with less x's? Or what's kind of unique about a parabola, where I can cut it in a certain spot that'll give me all the same values? It's symmetrical, perfect. So that axis of symmetry thing, right, that we've talked about with that negative b over 2a, we know that if we were to cut it right down the middle, all the y values are the same on the left as they are on the right. And so if I restrict this domain and I only look at the x values that are positive of that axis of symmetry, or the vertex, then I will still have the same y values while I've preserved my range while restricting the domain and creating a one-to-one function. Okay? So now this piece still has all the same y values. It doesn't have the repeating side, so it is a one-to-one function. It passes both the vertical and horizontal line test. And then we'll have all those y values. So let's look at its new domain. So my new domain that I'm going to restrict is all values that are greater than or equal to that negative 5. So from negative 5 all the way to infinity. And then my range, which I've preserved, is going to be still from 0 to infinity. Okay? So now I still have that range intact. I've just restricted the domain. Now what we're going to notice is as we go to take the inverse of this, okay, so we would flip-flop, we have x equals the quantity y plus 5 squared. Undoing a square involves a square root. So the square root of x. And then we have y plus 5, so then we'll have to subtract 5 from both sides. So square root of x minus 5 equals our new inverse function. If we look at this graphically, we're going to be shifted down 5 units. 5. And then we have the square root kind of shape to it. That's what we're used to seeing, right? And then we also kind of remember that you have the plus or minus, so there's kind of that other piece that we usually don't graph. Now we'll kind of notice why that happens. So if I had taken just this restricted domain piece and reflected it, it's going to actually turn into that square root piece that we normally just graph. And so let's look at just the solid line there. What's its new domain and range? So my domain is from 0 to infinity. What does that look a lot like? Hopefully we start to connect that that is all the y's from the previous, right? Those match up. And then all of our ranges are going to be from negative 5 and greater, which matches up with all the x's from the original. So our x's and y's literally are all flipping. So your domain and range you see actually does completely flip-flop. So that's one of those patterns we'll start to recognize. So you'll have to state the domain and range of the original, restrict the domain so it is one-to-one, and then with the new inverse function again, find that equation and state its domain and range. So we start to recognize that pattern that with these inverse functions, everything gets flip-flopped. All the x and y's get completely flipped. Okay? The rest of the stuff we're going to look at tonight is going to be proving algebraically that something is an inverse. And we're going to do that using composition of functions. So again, if you haven't seen compositions before, or if it's been a while, this is that f of g of x stuff, which sometimes they call the fog of x, because that's how they write it, is with that little open circle. I personally like seeing the notation this way, where it's f of g of x. Is literally what you're doing is you are taking g of x and you're plugging it in for x in the f of x equation. So if I was to look at something like 53, we're going to see that our f of g of x is going to equal -2, and where we see x, we're going to plug in g of x. So this becomes x minus 5 over -2 plus 5. And what we're expecting, if this is truly an inverse, is that we're going to have this composition that brings us back to the line y equals x, which is that thing we've reflected across. Okay? So -2 times the quantity x minus 5 divided by -2 will give us x minus 5 plus 5. And so we see, yes, in this case, f of g of x equals x. And this is, in fact, the true inverse. Okay? So as we see things that are getting reflected across y equals x, when you get the composition of the two equations, it presses it into that line we're reflected across. Okay. And so the last piece will be find the inverse of an equation and then prove to us that it is the composition, or is the inverse by taking the composition. So the last piece you'll see will be something like this. So if we did 61, we want to have x equals 3y minus 5. So taking the inverse, flip-flop our x and y's. X plus 5 equals our 3y. So x plus 5 all over 3 should equal our inverse function. So as we go to find the composition then, so our f of g of x, if this new composition is g of x, is going to be 3 times x plus 5 over 3 minus 5. And as we work through that, we get x plus 5 minus 5. So this again just equals x. So we can confirm that we did that correct, and we do have the true inverse. Okay, that's what we'll work on.